Hi everyone, this is Dr. Waite. Here's an announcement slide that we'll go over before getting into the lecture. First of all, this is the second class of the semester for the 28th of August 2019. Hopefully everybody got the announcement that we weren't meeting in person today. I hope that nobody was sitting there in the classroom wondering where the instructor and all his classmates were. So the first things first, if you haven't already obtained the textbook, please purchase or rent that as soon as possible. It's a very valuable resource, and although the homework assignments are going to be assignments that I myself have prepared independently, it's still really important for you to have the textbook for the data that's in the appendices, for the information that describes the concepts. So the book is cheap at this point. The 10th edition is available for purchase or rent for a very reasonable price, so I encourage you to obtain that as soon as possible. As I hope you heard in the first lecture, homework number 1 is already posted on MU Online. Now you've got some time to work on that. You're not going to have to submit that until before class on Thursday, September 5th. And so you have about a week, if you're watching this on Thursday, the 28th of August, you've got about a week to finish that assignment, including some time after I get back on campus. I'll be back on campus on Tuesday, September 3rd, and so you can come visit me in my office if you've got questions and want to go over things on that homework assignment. But I do things a little bit differently maybe than some of the other instructors. You're going to be submitting the assignment as a PDF file to MU Online. You can't email the file to me. You can't turn in the paper assignment. I only accept homework as a electronic version, a PDF file where the entire assignment has to be in the same single PDF. So don't make it multiple PDF files. Don't upload a JPEG. Just for ease of the grader being able to review your assignment, it has to be that way. If you have any questions about the submission approach, then please let me know. I find that the Cam Scanner app, which is available both for Android and iPhone, is probably the best way for making PDF files. And when you do make PDF files, please submit them as black and white, not color. Okay, today's lecture is previously recorded in a past semester, but the material itself is the same from those past semesters until now, and so it's still going to be applicable. I've edited out the announcements from that previous semester, but there may be some incidental references to time that maybe doesn't quite match up, and you can just ignore that. These are the announcements that you need to be aware of. The subject of the lecture is fluid properties, elasticity, viscosity, gas laws. All of these topics are covered in the homework assignment that's going to be due on Thursday, the 5th of September. So I hope you'll pay close attention to the lecture. And another suggestion that I'll offer right here at the beginning is that as I'm working through an example in the lecture video, I'd encourage you to pause this recording. You're watching this on YouTube, and so you know how to pause the recording. And in your own notes here in front of you, in front of the screen, I'd encourage you to try solving the problem. So that means you need to have a calculator handy, a writing instrument. I hope you're not just watching this and kind of tuning it out while you do something else, but you'll get your best results and you'll be most properly prepared for the homework assignment if you've actually worked through the examples that are included in the lecture. So I hope you'll take that advice to heart. Please let me know if you have any questions, either with the material or with the announcements. I don't know if Dr. Yoon has already mentioned to you, but I'm going to be out of the country, and so it's going to be a struggle for me to respond to email messages with the time differences and everything. But if you do have an urgent issue that can't wait until I'm back on campus, I'd be glad to do my best to address that. And that's it for now. I'll see you in person on Tuesday, September 3rd.
One of the good places to start is a discussion of units. And actually, if you have the textbook, on the front cover is a conversion. It's a list of conversion formulas between SI and traditional units. And we'll use both in fluid mechanics this semester, and probably we'll use SI units a little more frequently than we'll use the traditional British gravitational units. Of course, in the SI units we have kilograms, and in British gravitational units we have pounds mass, or slugs, as our units of mass, whereas we measure units of meters, And that's feet, inches, yards, miles. I always get a lot of laughs. I've taught overseas before. I've taught outside the United States. And when I tell them about the unit system that we use in the United States, they always scratch their head about 12 inches in a foot and 3 feet in a yard. They just think it's so ridiculous. And, it is kind of ridiculous. Luckily, there aren't traditional seconds. Think of how weird that would be, as if there was SI time and there was traditional time. Who knows, maybe there'll be metric time later on where there's 10 hours a day and 10 seconds in a minute. Maybe there already is, but I don't know it. Where things get a little bit muddled is where we start to talk about units other than mass, length, time. Because all other units are derived from some combination of mass, length, and time. So a units of newtons, for example, is a kilogram accelerated 1 meter per second squared. A pound force is the corollary to that. We'll talk about how pounds force and slugs interact in just a second. For gravity, we'll use 9.81 for our SI, gravitational acceleration. Oh, do I not have 32.2? Well, it is. 32. Oh, here it is. All right. So pounds mass versus pounds force. Now, if we're working in SI units, a newton is the amount of force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. Now, in traditional units, instead of kilograms, we've got pounds of mass or slugs. So a pound of force is how much force is required to accelerate one slug at a rate of 1 foot per second squared. And a slug is 32.2 pounds of mass, which doesn't make a lot of sense until you remember that gravity is 32.2 feet per second squared, and so that's our gravitational acceleration. And so when you have gravity, when you have Earth's gravity, then a pound of mass exerts 1 pound of force. But if you're talking about any other acceleration besides gravitational acceleration, then 1 pound mass and 1 pound force aren't necessarily the same thing. But a pound of mass does exert a pound of force when it's just stationary on Earth, where we've got gravitational acceleration of 32.2. So, I mean, this won't be an issue a lot. We will occasionally have to remind ourselves what a slug is and how many pounds force it takes to accelerate a slug and so on. This is part of the reason why we work most of the time in SI units, is in the context of fluid mechanics, it just kind of like makes more sense a lot of times. All right, so weight is the effect of acceleration on mass. Today in lab, you're going to be examining fluid properties according to how much they weigh and trying to estimate the weight and mass of a liquid in a certain container. We'll be doing a brief hands-on activity in lab today and tomorrow. Temperature becomes important in fluid mechanics, particularly when we're doing stuff related to gases. And who here remembers back from chemistry the ideal gas law? I don't see as many hands as I expected to see. The ideal gas law, if there's one thing you remember from chemistry, as far as fluid mechanics goes, I hope that would be it. It'll come back to you. If you don't remember it, it'll come back to you. But we'll work in units of Kelvin a lot when we're doing gas stuff in fluid mechanics. And just as a reminder, the temperature scale of Kelvin, you have to add 273 to Celsius in order to get Kelvin. And the units of work and energy, we measure those in joules. And a joule is the amount of energy required to exert a newton of force over a length of a meter. Now power is when we put a time aspect into the exertion of energy, and so it is how much energy is being consumed in a unit of time. And so a joule per second is a watt in the SI system. Okay, now like I mentioned, there's a lot of units conversion in the front of the book here. I'm also going to print out a units conversion that comes to you from the reference manual that's supplied for the Fundamentals of Engineering exam. Have you all heard of the FE exam before? You're aware that someday in the not too distant future, you're going to be sitting down in front of a computer to take that first engineering licensing exam called the FE. And so I'll give you a conversion sheet that comes from the FE, and you can use that conversion sheet during the exams, just to start to get you familiar with what the equations look like in that supplied reference manual, because it's really important for you to do well on that exam. Converting temperature, for instance, from Fahrenheit to Celsius is kind of weird, not only because the boiling point of water is different, but also the size of a degree is different. Fahrenheit degrees are smaller in size than Celsius degrees. They're only 5/9 of the size of a Celsius degree, in addition to the difference in freezing temperature and boiling temperature. We'll have an example in just a moment where we do some temperature conversions. In the gas law examples, if you're working in the traditional units, you have to use units of Rankine, and that's the absolute temperature scale for the British gravitational units. And over the summer, I started getting into baking, of all things. I don't know why, but just all of a sudden, I decided I wanted to try sourdough bread, making sourdough bread. And it's really interesting. I could go on and on about sourdough bread, but one of the things I'll tell you is that temperature is really important when you're making sourdough bread, because you're not just adding external yeast, you're actually trying to use your own yeast that you develop in a small culture, and then, see, here I go. But temperature is important in baking, and so I found myself over the summer doing calculations of, if you're adding flour and water together and they're both at different temperatures and you want the mixture to be a certain target temperature, how much heat do you have to add to the water? And so I was using absolute temperature because you get your calculations to work out when you use absolute units of temperature. That it wouldn't work out if you were using the relative scale of Fahrenheit like it would for Rankine. So, all right, just as a give me a break from talking and give you a break from listening, let's try an example. If it was 46 degrees Celsius in Dubai last Wednesday, what was that in Rankine? So we need to do a temperature conversion here, and this is a multi-step temperature conversion. You're going to be going both from Celsius to Fahrenheit, and then from Fahrenheit to Rankine. 46 degrees Celsius. That sounds like nice and cool, right? No, it's extremely hot. All right. Now, I realize that a temperature conversion like this is as easy as just speaking the question into your smartphone, and then Google will automatically convert it for you. But they don't let you ask questions into your smartphone during the FE. So you actually have to know how to do this stuff. So we start off with 46 degrees Celsius. And remember, Celsius degrees are larger than Fahrenheit degrees. And so this 9 degrees Fahrenheit for every 5 degrees Celsius, we have to multiply this ratio to convert the number of Celsius degrees into the number of Fahrenheit degrees, and then also make the adjustment in the freezing point, because whereas Celsius, the freezing point is 0, the freezing point is 32 in Fahrenheit. So the conversion is kind of 2 stages, adjusting the size of the degrees and also adjusting the freezing point of the water. So if it's 46 degrees Celsius in Dubai, then people are enjoying 114.8 degree Fahrenheit weather. And that's summertime weather in Dubai. The conversion from Fahrenheit to Rankine then is just adding 460, which is the number of degrees. You have to go down from 0 Fahrenheit to get to absolute 0 in the Rankine scale. So everybody feel good about this one? Any questions? All right. Great. Now, fluid properties. We're talking about fluid properties today, and probably everyone's already familiar with the idea of density. And so a fluid that has a high density is something that would have a lot of mass per unit volume. And so can anybody think of a fluid that's kind of famous for having a high density? Mercury, right. It's a fluid that when I was real young, you kind of got to play around with. You know, you'd break open the thermometer to play with the mercury, but those were in the carefree days. Now, with modern safety regulations and everything, they put alcohol in the thermometers. I guess that could be fun too, but not from the standpoint of playing with mercury. So, yeah, mercury has a lot of mass per unit volume. Water has a density of 1,000 kilograms per cubic meter. Now, it varies as a function of temperature. And in the back of your book is a table that has fluid properties as a function of temperature. So if we go to appendix, I think it's A5, that has the fluid properties for water. Let's see if we can find it. There it is. All right, so A5 is the physical properties of water. So you'll notice that it changes as a function of temperature. So the density decreases as the temperature goes up. Anybody want to guess? Why do you think the density decreases as the temperature goes up? What's going on? The volume is changing. Yeah, so heating up water doesn't make its mass change. I mean, it would have to be one of these two things. If the density is changing, either the mass is changing or the volume. So like we take a kilogram of water and we heat up that kilogram of water. It doesn't become 1.1 kilograms because we heat it up. But what it does do is it changes its volume. And so it's going to increase the volume as you warm the fluid, and that's going to decrease the density since volume is in the denominator there. So fluids, liquid in particular, vary their density as a function of temperature. Now, a lot of the problems you solve this semester aren't going to specify what temperature it is. You know, the problem sometimes will say 80 degrees Celsius water, and if it says some specific temperature, then you should go to the table and look up the density for that temperature. But if it doesn't specify, then just use the default assumption of 1,000 kilograms per cubic meter. That'll be sort of our standby water density. And if we're working in traditional units, then our standard density is 1.94 slugs per cubic foot. Of course, because what else could it be, right? All right, so that's mass density. Specific weight is related to mass density, except that instead of kilograms per cubic meter, we're talking about how many newtons of force are exerted by the fluid per unit volume. So using water as an example, water has a specific weight of 9810 newtons per cubic meter. Now, there's a familiar ring to the 981. What does that remind you of, 981? Gravity, right. So we go back here to the formula. It's saying that specific weight, sometimes this is also called unit weight. So it's saying specific weight is just density times gravity. And we'll use specific weight a lot in the equations that we solve because it plays an important role in everything from fluid hydrostatics to the acceleration of fluids. And so just multiplying the density times gravity can give us that specific weight. And so it's the weight of a fluid per unit volume. So water, if we have a cubic meter of water and we put it on a scale that's reading out in terms of the weight, which is a measure of force, it would say 9810, or if we had a cubic foot of water, then it would be 62.4 pounds of force is the force that's exerted there. All right, so maybe this is the first unique information. All the other stuff, I guess, is review from other courses, but maybe you haven't yet seen specific weight before. So there's your formula. Gamma is the density times the gravity. Compressibility comes into play here because it's one of the ways that we distinguish between fluids that are gases and that are liquids. And so comparing two common fluids, water and air. One of them is compressible and one of them is not. And so water is generally considered to be incompressible. Now actually, it's a little bit compressible, water is, but it requires enormous forces in order to compress water. As compared to air, air compresses really easily. When you drive around in a car that has compressed air in the tires, it's no big thing to compress air. But just the fact that we usually say water is incompressible, that doesn't mean that its density is always the same. Because, of course, we already talked about how density changes as a function of temperature. But then also, we can add salts and dissolve other things besides salts. We can dissolve things into water, and then that changes its density by increasing the mass that's in a certain unit of volume. Salt water, for example, has a different density than water does because it's got added salts in there. And so salt water has a density, instead of 9810, salt water has a density of about 10,000, slightly higher than 10,000, typical seawater. Specific gravity is when we measure the relative density or the relative specific weight of a fluid compared to water. So we talked earlier about mercury. Mercury is that fluid that is unusually dense. Mercury has a specific gravity of mercury is 13.56. So what that means is it has a density of 13.56 times the density of water, which we already know is 1,000 kilograms per cubic meter. And so a cubic meter of mercury would weigh 13,560 kilograms rather than 1,000 kilograms like water does. And so what this specific gravity is we're just trying to compare things to water as our baseline. And it doesn't matter if you have the ratio being a ratio of specific weights or a ratio of densities. So we always think about how oil floats on top of water, right? So the fact that it floats on top of water helps us to know that it's less dense than water. And so oils would have a specific gravity of less than 1 because the density of an oil would be less than the density of water. So sometimes it can be confusing in the problem statement because specific is a word that both can go specific weight and specific gravity. But there you've got the formula. You'll figure it out. We'll start to use it, and then the confusion that you may feel now will gradually go away as you work more and more problems related to these. Any questions about these fluid properties so far? I'll try and keep an eye on time. I don't want to keep you late on the first day. That'd really be starting things off on the wrong foot, wouldn't it? I'll try to actually never keep you late. Here's what I aim for. I aim to start exactly on time and finish exactly on time. And I hope that you'll be here on time too. It really helps me out a lot because I'm so easily distracted if people aren't coming in and going out during the class lecture. So if you're here on time, I really appreciate that, and it'll help me. And if you're going to be late, you can always just watch the video, right? So yeah, don't come in late. Here's the table of fluid properties that I was mentioning. For those of you who don't have the book with you today, who didn't find it, those fluid properties are back in the appendix. This is table A5, which is for water. And it's showing both the density and the specific weight as a function of different temperatures. All right, here's the last topic we're going to discuss today, and that is the fluid property of elasticity. Now, just moments ago, I told you that water is incompressible, right? Well, here's the first time I'm contradicting myself. You didn't even have to wait like 5 minutes. Water is kind of compressible. And the way that we can measure how compressible a fluid is with a property that's known as the bulk modulus of elasticity. And what that specific parameter relates is it relates how much pressure is required to have a fractional change in volume. And I mean something specific by a fractional change in volume. What I mean is the amount of change of volume relative to the initial volume that was there before the compression began. I've got a calculation example here that I think will help to illuminate things, but this bulk modulus of elasticity tells us essentially how much pressure you need to affect a change in volume occupied by a mass of fluid. The bulk modulus of elasticity for water is 2.2 times 10 to the 9th pascals. That's really high. So it requires an enormous change in pressure to have a small change in volume. Now another way to think about this formula is, so dP is a change in pressure. So we can kind of like expand out this formula to say that the bulk modulus is the ratio of the change in pressure up here in the numerator, and then the fractional change in volume is going to be the initial volume here in the denominator of the denominator, and the dV. So you can have the dP is going to be some pressure that's applied. So let's take this as an illustration. Let's say that we started off with a sample of water that was 50 liters in volume, and it's open to the atmosphere. And so the 50 liters is our initial starting volume. And since it's water, we already know the fluid property that's going to be applicable here, the E sub V. We want to know what's the final volume that it occupies after we apply a pressure of 5 megapascals. So that's 5 times 10 to the 6th pascals that's being applied. So that's the delta P. And so delta P is the 5 megapascals. We can solve for the delta V that occurs and then apply that to the initial volume to find the final volume. So again, let me pause the recording, give you a few moments to calculate and collaborate with your classmates, and then we will revisit this to see if you get the right answer. Well, enforcing is probably too strict a word for it. I mean, sometimes I'll see students do, like 49.88654321874, and I'll be like, come on.
It's like a reasonable.
Yeah. All right, so what we do here is, first of all, our governing equation is this relationship between elasticity, change in pressure, and unit change in volume. So that's our governing equation that's given. We're given the initial volume of the sample, the fluid property that we need, and the pressure that's applied. And in the problem statement, it was using these, you have to know megapascals. You know, the interpretation of that is 5 times 10 to the 6th. So hopefully those already spring to mind. If not, then those are also in the FE reference manual that I'm going to be giving you. It reminds you all the engineering prefixes, you know, giga, mega, and so on, micro, nano. So rearranging the governing equation, because what we're going to want to solve for is this incremental change in volume, the delta V. So this negative sign that's remaining in the equation. What that negative sign means is that if you have the pressure increased, then the volume is going to decrease. So it's just kind of giving like a quantitative basis to what you'd already know on an instinctual level, that if you're compressing a liquid from all directions, it's not going to get bigger, it's going to get smaller. So that's what the negative sign there means. And so we have this delta V means it's the change in volume as a result of applying this pressure. So the change in volume is 0.114 liters. And so the final volume, 49.886 liters. And then what we could do, I guess if we're being careful about the units, it looks like we've got three significant figures here. 50.0 liters, 5.00 megapascals. And so my preference would be that you kind of like show all of the digits of accuracy that you've got, and then in the end you could round to 49.9 liters. So, you know, if you were measuring this with some sort of a scale that was only accurate to the nearest tenth of a liter, then what you'd see is 49.9 liters. But depending on the precision of the scale you're using, maybe you'd be able to read it to more digits than that. Anybody know what this is? What are we looking at a picture of here? Honey. How did you know it's honey? It's not labeled. What are the clues that that's honey? Okay, the color first of all. Yeah, it's... Okay, viscosity. What do you mean?
The thickness.
The thickness, yeah. So this is a metal spoon, presumably, and they're pouring it out of the spoon, and you can kind of just get a sense from this photo, even though it's not a video, it's a photo, you kind of get the sense that it's pouring slowly out of that spoon, right? It's sticking together. And it's not, you know, honey is sticky, but viscosity is something separate from that. You can have a viscous fluid that isn't like also sticky. Like if you got it on your hands, a fluid doesn't have to be sticky to be viscous. Think of like motor oil. Motor oil, for instance, is more viscous than water. And although it's slippery, it's not tacky because it doesn't have sugar in it. These little air bubbles are also clues that it's got it's highly viscous. Because if this was just water, those air bubbles would rise to the surface, but they're trapped. They're entrained in the liquid. And so that's kind of another visual clue that what we've got here is a highly viscous substance. So let's watch this video clip. Oh, hold on, this is going to get me kicked off. I gotta do this. The glycerin was deforming very slowly when the container was tipped over. So the definition of strain, you've all taken mechanics before, solid mechanics. The definition of strain is the deformation of a physical body under the action of applied forces. So for instance, if I had a metal ruler, normally I bring a metal ruler to this class, I forgot. If I was pushing a metal ruler on the ends, it would start to bow and deform. And the harder I push, the more it's going to deform. So that's an illustration of strain, is that deformation under the forces that are applied. So the stress is the force I apply, the strain is the response. In a solid, then the proportionality of the stress and the strain we call shear modulus. Hopefully that rings a bell. And one of the ways that we differentiate between solids and liquids is that in the case of a solid, it stops deforming when it reaches an equilibrium between the stress and the strain. But in a liquid, it's going to continue to deform as long as the stress is applied. Like if I had a tank of water and a propeller that's turning inside of that water, I'm going to be applying a stress and it's going to keep deforming. It's not going to just deform one time and then stop deforming. As long as I apply a force, it's going to continue to deform. Now the proportionality factor in solids, instead of calling it shear modulus, in fluid mechanics, we call that the viscosity. Now, specifically, sometimes it's called the absolute viscosity or the dynamic viscosity. And those three terms all mean the same thing. Whether a problem statement says dynamic viscosity or absolute viscosity, or if it just says only viscosity, it all means the same thing. It's talking about how much a fluid deforms under the application of a certain amount of force. So the stress and the strain. The strain is the response. The stress is the force that's applied. So this is a picture of a stream, and sometimes what we'll use the understanding of viscosity for is to characterize a velocity profile. In a river, let me draw just kind of like a cross-sectional view of a river, and we'll talk about how viscosity relates to that. So here's a river going downhill, and here's the water. The speed of the movement of the water isn't the same at every depth. It would be wrong if we assumed the water was all going the same speed at the top and at the bottom. More realistically, what's happening is that the water that's very close to the bottom is going slow, and it progressively increases in speed so that there is a velocity profile that looks like this shape. And part of that is because at the bottom of the river there's rocks and whatever the surface is made out of, whether it's rocks or clay or a smooth concrete surface, regardless of what the material is, it's applying a resistance force to the water in the opposite direction of the water's movement. And so the shape of that velocity profile is influenced by the viscosity of the fluid. So here is an image of that same velocity profile that I've drawn on the board here, but what it shows is a certain distance up from the bottom of a channel bed, and the velocity is increasing the further away you get from that surface of resistance. So the unmoving surface at the bottom, you can't have water slipping over without any frictional losses. So we call it, the phrase is the no-slip condition. The no-slip condition. So what the no-slip condition is that there has to be, the water will have the same velocity as the surface right at the interface between the two. The water actually has a velocity of 0. That molecule that's just above the water, the channel bottom surface has the same velocity as the channel itself, which is motionless. But then the further away you get from that point of friction, the velocity increases. So we can think of that maybe as a river. Now, let's look at this video clip that illustrates, again, I think I better pause this. I got to keep remembering to turn that on. All right. So the terms that we're going to be using, the viscosity is the resistance to the flow, the v is the velocity, the distance up from the bottom, and now the rate of strain is the ratio of the slope of the line of this curve. So dv dy. Remember that dynamic viscosity, absolute viscosity, or just using the phrase viscosity by itself, those all mean the same thing, and we're using the variable mu for that, and it's the Newton seconds per meter squared is the units that we're going to use most often. If you go to the back of your book in the appendix, then it has those units for viscosity. And shear stress, the way that we can calculate the force that's applied is by normalizing that on a unit area basis. And it's the stress that causes strain, which is the deformation. And here is the formula that relates the viscosity of the fluid to the rate of strain and the shear stress that's applied. Now this is an important formula, but the next formula I'm going to show you is even more important, because what it does is it takes this shear stress and we calculate shear force by multiplying the area that the shear stress is applied over. So let me show you what I mean. Before we get to that, just think about, in terms of viscosity, it's easier to walk through air than it is to walk through water. But the question is why? Like if you've ever been in a swimming pool, you know that you can't walk through the water in the pool as quickly as you can walk through air. And anyone want to venture a guess why that is?
The water provides resistance to you.
Good. So the water provides resistance. But why does it provide resistance? What's happening? Like think about your leg and the fluid.
You're displacing the water.
Okay. So right now I'm displacing the air. Like as I move through the air, it's getting out of my way. It's deforming. But if I'm walking through water, it also has to move out of the way, but there's more resistance to the force that I'm applying. So what we can say is that there's less friction in air, and the rate of deformation is greater than the rate of deformation for water. So air moves out of your way at a quick rate when you apply a certain shear force, and we don't have unlimited strength to push the water out of the way at the same speed that we normally walk through air. So we could graph that, actually. We could graph for a certain shear stress that you're applying. Think of that as a force. The amount of force that you're applying to the air, there's a lot of deformation for a certain shear stress. There's lots of deformation for air, and very little deformation for water, and even less for oil, for that same amount of shear stress that is applied. Now, viscosity is what we're saying is it's the slope of this line. For the amount of shear stress that's applied, how much deformation was there. And so this is saying A is the rise, which is the shear stress. B, which is the run on that slope, it's du dy. And du dy is deformation. Or in other words, back to that curve on the previous slide, du dy is, we could do a graph of this velocity distribution. And du is the change in velocity. dy is the distance away from some boundary. And we're going to use this. We're going to say, what is the velocity of the fluid? What is the difference between the distance between two surfaces? And we're going to use it to calculate forces. Okay, so think of velocity in two ways. You can think of it as graphically, it's the slope of this line where you're graphing shear stress versus the rate of strain. Or you can think of it as the ratio or the proportionality factor that ties in this equation the two variables together. So this viscosity relates shear stress and rate of strain. There is one other phrase that you need to be aware of. I already told you that absolute viscosity is the same thing as dynamic viscosity, and sometimes we just say viscosity. Those three things they're equal. Kinematic viscosity is different. Kinematic viscosity is used sometimes because a lot of formulas have both density and viscosity in them. And those formulas that have both of those variables, we might as well combine it into a single factor, especially because sometimes viscosity is related to density. And so to simplify that, the kinematic viscosity is the absolute viscosity divided by density. So here's the formula for kinematic viscosity, and you can go to the table in the back of the book and look up the kinematic viscosity for water, air, and other fluids at a variety of temperatures. And the units, if you see how the units cancel out, the dynamic viscosity was going to be Newton seconds per meter squared. Of course, we already know that kilogram per cubic meter is the units for density. And so since a Newton is a kilogram meter per second squared, if we're going to expand out that Newton into its base units, where all units are essentially made up of mass, length, and time. Those are the only three base variables that all other units are constructed from. So if we expanded out the newtons into kilogram meter per second squared up in the denominator and then canceled out everything that is like, then the kinematic viscosity has units of meters seconds per square. I'm sorry, meters squared per second. So just to clarify, these three terms are all viscosity, but kinematic viscosity is different, and we get it by dividing absolute viscosity by density. Okay, so shear force is shear stress multiplied by area. So therefore, that means if we know that shear stress, tau, is going to be the viscosity times the rate of strain, then we can get the shear force by multiplying the shear stress by the area that the shear stress is applied over. And so this all works out. If we're a stickler for the units, and we should be, then the units of force are newtons, and we get those units by having a shear stress applied by multiplied by an area. du is going to be meters per second because u is a velocity. dy is an incremental distance, so it's going to be units of meters, and so all of that cancels out into units of newtons. Now this formula is really important for the homework that you're going to be solving, and so if we take a look at how to apply it, what we often do is just simplify this rate of strain term to be velocity over distance. And let me show you what I mean by that. We can do that when we assume a linear velocity distribution. And so let's say that we have a tank full of that liquid from the video, the glycerin. Glycerin was the one where it was shaken, it hardly moved at all. When it was inverted, it poured out really quickly. That was the glycerin. So if we had a tank of a viscous fluid and we're going to drag a plate through that tank, let's say it's a metal plate with dimensions of 3 meters by 2 meters. So I'm not sure which dimension we're seeing here. I guess this is the side view, and so it's probably, let's say, oriented like this. It is 3 meters long, 2 meters wide, and we're going to be pulling it through a fluid. Now when we pull it through the fluid, remember the no slip condition means that the fluid is going to be holding on to that solid surface. And so even when we apply a force, it's going to be moving slowly because the fluid particles have to deform in order for this to move. So we know the area of the plate, we know the viscosity of the glycerin that it's being towed through, and we know the velocity that we hope to achieve, velocity of 0.58 meters per second. Now, these distances from the top of the tank and the bottom of the tank are going to be important for us because we're going to calculate the overall net force. But the way it works is that there's a force on the top and also on the bottom of the plate. And so we have this tank, and here's the plate that's being towed. So the distance to the top of the plate is 1.2 meters, and the distance to the bottom is 2.4 meters. We're going to calculate the force, the shear force on the top, and the shear force on the bottom. And substituting it into this formula that we're given, which is area times viscosity times the incremental velocity. So I'm going to say delta V divided by delta Y. All right, and the bottom is the same formula. The difference between the two being that the distances, the delta Y, is going to be different from the top and the bottom. Okay, so for the top, the area that we're using is 3 meters by 2 meters. Okay, the viscosity of the glycerin we're given is 0.15 Newton seconds per meter squared. Newton seconds per meter squared. And the dV is 0.58 meters per second. And the dy, so from the plate to the top of the tank is a distance of 1.2 meters. And we can do that same approach for the bottom. So there's 6 square meters of surface area on the bottom of that plate. It's still being towed through the same fluid of 0.15 Newton seconds per meter squared viscosity. And then the incremental velocity is 5.8 meters per second. And the distance is 2.4 meters. So calculate those two forces. If you've got your calculator here today, and I hope you do, let's find out what is the force on the top plate, the force on the bottom plate, and therefore, what is the total force that we have to apply in order to move that plate through the fluid.
This is more like a conceptual thing, but could that force be applied anywhere on the top of the tank?
We're not applying it onto the tank. It's the force required to get the plate to move. So what we're calculating is, we're pulling this way on the plate, but then what the fluid is doing is the fluid is pushing like this way to resist that movement. And so it's really about the fluid is deforming, and that's where the force comes from. So the place we're applying the force is, we assume there's maybe like a string of some sort on the leading edge of that plate as it's being pulled through the fluid. Yeah, so the forces on the top of the plate are higher because the distance between the plate and the next surface is less. Okay, so some other things about viscosity that we're going to address is that viscosity as a property is independent of pressure. So that means that the viscosity at the bottom of the ocean is the same as it is at the top of the ocean, that the pressure being experienced by the fluid doesn't affect its viscosity. And what causes viscosity is molecular cohesive forces. So in a liquid, as you warm up a liquid, what happens is that the fluid becomes less viscous because the molecules are moving around more quickly, and then that decreases their cohesive forces. But ironically, in the case of a gas, viscosity for a gas increases with temperature. So gases become more viscous as they're heated up, not less viscous. Who here has changed their own oil before? Almost all of us. All right, great. So you know that the oil pan empties a lot more quickly if you warm up the engine first. Because the reason you do that is by warming up the engine and warming up the oil, the viscosity decreases when it's warmer, and then it flows more quickly out of the engine. So in the case of a gas, what that means is that actually if you have more gas, because the molecules are bumping into each other, they have a lot more collisions, and the velocity of those collisions is higher. The gases are kind of getting in the way slightly more, and so the viscosity and viscous resistance is greater as the temperature goes up. Another thing that you need to know for the homework assignment is Sutherland's equation. Sutherland's equation is a way to estimate the variation of gas viscosity. Sometimes you can just look up out of a table the viscosity for a certain temperature that you want, but then there will be other times where you don't have a table available, and so what you can do is you can use this equation to estimate the viscosity at other temperatures. So Sutherland's equation would be used, for example, on a question like this. The viscosity of air is 1.95 times 10 to the minus 5th Newton seconds per meter squared at 50 Celsius. So what is it at 95 Celsius? So in this formula, the viscosity at the original temperature is this one. The temperature at that given temperature is put in, and we have to solve these in Kelvin, because remember what I said in the previous class, for most of our gas-related problems we have to use an absolute temperature scale. So although the temperatures in this example are given in Celsius, the first step is to convert to Kelvin, and another hint that you need to do that is that Sutherland's constant is itself in terms of Kelvin. So if you're going to be adding S to the given and desired temperature, the temperatures have to be in the same scale to be able to add them together. So I'm going to pause the recording and stop talking for a second, and what I'd like you to do is try and determine what is the viscosity of air at 95 Celsius. And remember that the conversion is you have to add 273 to get kelvins from Celsius. Okay, so remember that the purpose of this equation is to estimate viscosity of a gas at some temperature where you don't have the value known from a table. So you have to start with the value where you do know the viscosity, and in this case we know the viscosity at 50. So what we're saying is the original viscosity at 50 was 1.95 times 10 to the minus 5th Newton seconds per meter squared. And then we multiply that by the ratio of the temperatures to the 3/2 power, where we've converted the temperatures to the absolute scale. Technically it's 273.16 is the Kelvin version of 0 Celsius. So to convert between Kelvin and degrees Celsius, we add 273.16. So we know the initial temperature, we know the temperature that we desire to know the viscosity at, in this case 95 degrees Celsius, and then we also have this term where we add in Sutherland's constant, 111 Kelvin. So did anybody else get 2.15 times 10 to the minus 5th Newton seconds per meter squared? Okay, good. You'll notice that when I do these examples, I include the units, and I'm going to do that for every example we work through the entire semester. And next semester, when you have me for hydraulic engineering. I'm always going to include the units because, number one, it's easier to avoid mistakes if you write the units. Like, let's say, for instance, that I had forgotten to convert from Celsius to Kelvin. If I wrote the temperature in Celsius, then I'd right away see, oh, I can't add that Celsius to something that's in Kelvin. So if you include the units, one advantage of doing that is that it helps you to prevent errors. And then the other advantage is that by canceling out the units and making sure that everything's dimensionally consistent, you can ensure that you use the right formula in the way that it was intended. The other thing I'll mention about this solution is that I have intermediate steps. Like, it's really easy when you're putting things into your calculator to kind of lose the broader perspective. So rather than do everything just in one calculation and get the final answer, what I did was I solved, all right, what's the answer of inside of these brackets? Like the 368.16 divided by 323.16. That's 1.139. So I just did like part of the problem in one step. Same thing here. I found the result of that addition and ratio. And then as the final thing, I did the multiplication and the power step. And by having it kind of showing your work step by step, then you can double check it more easily. Like, I can just verify that I had the right answer by doing these intermediate steps and making sure that I get the same values that I did the first time. Any questions about this example using Sutherland's equation? So Sutherland's equation is used because gas viscosity varies as a function of temperature. Let's look at that temperature variation. What we already know is that oil becomes less viscous as it heats up. What I told you just a moment ago was that air becomes more viscous as it heats up. The trend is fairly flat. It doesn't become hugely more viscous, but it does come a little bit more viscous. So that's kind of an interesting point of fact, that the viscosity increases. When we're talking about fluid properties, one of the things that we have to be aware of is the difference between Newtonian and non-Newtonian fluids, and this ties into viscosity. Let's start by just looking at a video clip that illustrates a non-Newtonian fluid. A non-Newtonian fluid is something where the viscosity actually responds to the shear force that's being applied. So the kid who's walking quickly, as he's jumping up and down on that fluid, the viscosity immediately under his feet is very high. It's viscous because a big shear force is being applied. But then this kid who wasn't moving very quickly, he was applying a low shear force, and so the fluid's viscosity was lower, making his foot able to sink down into the fluid because it was deforming easily. So let's look at this graphically. What we were just seeing was a shear thickening fluid. Most fluids, like water is a Newtonian fluid. So in the case of water, its viscosity is independent of the force that's applied. It has the same viscosity whether you're applying a little bit of force or a lot of force. But in these non-Newtonian fluids, like a shear thickening fluid, which we just saw, if you apply a big shear stress, then the shear strain becomes greater. There are shear thinning fluids, like toothpaste or ketchup is an example of a shear thinning fluid. And in a shear thinning fluid, it starts out with a lot of viscosity, but the more shear stress you apply, it becomes less viscous. And that's partly why in the case of a glass bottle of ketchup, you may know that you'd have to really hit the back of the ketchup bottle so much. Well, what you're doing when you apply that force to the back of the ketchup bottle, you're actually decreasing the viscosity of the fluid temporarily. So it can flow, and then it stops when there's no more shear force, and then you apply another bang to the back of the ketchup bottle, and the viscosity temporarily decreases. And so the fluid, in essence, is responding to the force that's applied. Let's look at this other clip. Okay, one last thing in the minutes that are remaining here. I want to show you the equation for how to use the ideal gas law for solving problems. PV equals nRT is probably something that you remember from chemistry class. But if we take the molecular weight of the gas into account, then we can solve problems using this formula here. If you've printed the notes, highlight this one, because this is the one that you need to solve problems like the example that I'll show you in just a second, which is also related to a homework problem you've got. What this says is that the pressure of a gas is equal to the density of the gas, R, which is the universal gas law constant. In this case, it's specific for the gas in question. And T is the temperature. Remember, you have to have temperature in kelvins when you're working with gases. So the example that I want to show you, I'll just put this solution on the screen here, and then if it would be helpful for you to work through it on your own time, you'll be able to do that by going back to the video recording. What we were going to do is we were going to determine the density, specific gravity, and mass of air in a room that's a 4 by 5 by 6 size. And so we've got a certain volume of air, and we want to know what's the density, the specific gravity, and mass. So the key to this is calculating the density first. The density relates to the pressure. And so in this room it says the pressure is 100 kilopascals. And so you put in 100 kilopascals. The R value comes from table A2. And then the T is the temperature of the gas, which you've converted from Celsius to Kelvin. So let me put here on the screen how you'd calculate, first of all, given all of these information that you'd convert from Celsius to Kelvin. Here's the R value, and just for fun, I show you what are the units if you break that down from joules per kilogram Kelvin into its base units. So you can calculate using that formula for density, the density of the gas. And then once you know the density, remember the definition of specific gravity is just the density of something relative to water. So here's the specific gravity, and then you could also calculate the mass of air in the room by multiplying it by the room's volume.